Today we're going to find areas of polar coordinate equations. We're going to start with the area of a sector and what we know about it. So in order to find the area of a sector that has a radius of r, so we're going to go out r through an angle theta, is given by 1/2 r squared theta. So you kind of think about really, the area of this piece of pizza here. So if I want to do the same thing for like a Calculus 2 class, I want to find the area of a fan-shaped region between the origin and this curve r is equal to f of theta, opening radially through alpha and all the way through beta. So when we're integrating in the beginning, what we do is we start by integrating with respect to x and then also with respect to y. So when we're integrating with respect to x, we're really sliding horizontally, so integrating this way, so very rectangularly. So we're sliding in the x direction, or we're going to be sliding in the y direction if we're going to integrate with respect to y or dy. But now we're integrating with respect to theta or using d theta. So this integral integrates more radially, or you can kind of think of it like a windshield wiper. So it's going to start at alpha and it's going to integrate through beta. So we're really opening up. So just like the quadrants 1, 2, 3, 4, we're opening radially in this direction. So that's where we start at alpha and then we end at beta. So using this equation, we're going to find the area between the origin and a curve from some alpha to some beta of really kind of one of our known polar coordinate equations. So let me pause this. We'll come back with the example. So the example I chose was to find the area from the origin to this radial function, or r is equal to 2 times 1 plus the cosine of theta. Now we're familiar with 1 plus the cosine of theta. It's this cardioid. But when we multiply it by 2, it's really going to radially stretch this thing by 2. And we're going to open up from alpha is equal to 0 to alpha to beta is equal to pi. And I want to show you what part of the this thing that we're going to be finding the area of. So when we have 0, we're talking about this. This is when alpha is equal to 0. And we're opening radially. So, we're opening like this all the way through till we get to finally pi. So this is going to be, beta is equal to pi. So really what we're going to find is we're radially finding the area of this thing, and if I want to kind of draw like radials, but we're finding the area of the top half of that cardioid. So in order to do this, we know that the area is equal to the integral from alpha to beta of 1/2 r squared d theta, where r is this function, so this is going to be equal to the integral from 0 to pi of 1/2 times, 2 times 1 plus the cosine of theta d theta. And this has to be squared. So just like with any integration, we tend to simplify the expression first and then we integrate second. So what we're going to have to do is we'll have to square first, and then we can multiply that by this half. So this is going to be equal to the integral from 0 to pi of 1/2 times, when I square this, the square of 2 is 4. And I'm going to have to square this binomial, so you're going to have to FOIL it. So 1 times 1 is going to be 1. Outside's going to give us a cosine of pi. Inside's also going to give us a cosine of pi, so plus 2 cosine of pi. And the last is going to be cosine times cosine, which is going to be cosine squared of theta. Theta. Now what happens with your polar coordinates is we tend to have to integrate this cosine squared, so we're going to have to use the trig identity 1 plus the cosine of 2 theta all over 2. So simplifying this is going to be the integral from 0 to pi of 1/2 times 4 times 1 plus 2 cosine of theta, and then this is going to be 1/2 plus cosine of 2 theta over 2, so breaking this apart, plus cosine of 2 theta all over 2, and d theta. So what I'm going to do is I'm going to combine these two, so 1/2 and 1 is going to be 3/2. And then finally 1/2 times 4 is going to be 2. So this is going to be equal to the integral from 0 to pi of 2 times 1, well actually not 1, we just said 1/2 is 3/2, so 3/2 plus 2 cosine of theta, and then we're going to have the cosine of 2 theta all over 2 d theta. Sending the 2 through is going to give us the integral from 0 to pi of 3 plus 4 cosine of theta plus the cosine of 2 theta all over 4 d theta. And all those things are easily integrable. So the integral of 3 is going to be 3 theta. This is going to be 4 sine of theta. And when you integrate this cosine of 2 theta, you're going to get the sine of 2 theta divided by 2. So it's going to be the sine of 2 theta all the way over 8. So this is going to be equal to 3 theta plus 4 sine of theta plus the sine of 2 theta all over 8. And then we're going to evaluate this from 0 to pi. So plugging everything in, 3 pi plus 4 times the sine of pi plus the sine of 2 pi all over 8 minus, now when you plug in 0, this is going to be 3 times 0 minus the 4 sine of 0, and then plus sine of 2 times 0, or just let's say the sine of 0 all over 8. And what we know is that the sine of 0 is 0, so that'll go away, and this will go away. So the lower bound evaluation is all going to be 0. And then similarly, the sine of pi is equal to 0, the sine of 2 pi is equal to 0. So this answer is just going to be equal to 3 pi. So next we're going to find the area bounded between 2 radial curves. And we'll set up the formula and then give an example. So what I want to do is I want to set up the formula for finding this radial bounded region. So we're going to be bounded from R1 less than or equal to R2, so between here. And then radially we're going to be bounded from alpha radially to beta. So what we can see is this is really just kind of an expansion of what we did before. If I can find the area from R2 to the origin, I can also find the area from R1 to the origin. So it's really just going to be the subtraction of those 2 radial areas. So this bounded region, this bounded area is going to be equal to the integral from alpha to beta of 1/2 R2 squared d theta minus the integral from alpha to beta of 1/2 R1 squared d theta. Now, since they share the same bounds and also the same angle of integration, we can put these together to be the integral from alpha to beta of 1/2 times R2 squared minus R1 squared d theta. So that'll be the formula that we're going to use, knowing that R2 is technically bigger than R1. Now, when we say bigger, we're actually saying further from the origin radially. So bigger happens to be this. Okay. So let me pause this. I'll put an example on here. We'll do one. Determine the area bounded or between the polar curves r is equal to 1 and r is equal to 1 minus cosine of theta. And I've drawn the curves over here so we can determine the limits of integration, and really we can determine what one's bigger radially and what one's smaller. So there's 2 different places that we could find the area. We could find the area over here between the 2 curves, or really this crescent moon shape as well. And for this one, I'm going to find the area between the curves on the right-hand side. I will discuss how to find the area on the right-hand side. All you have to do is just change the bounds, but you also have to change what function is bigger and smaller. So here, if I do a radial, let's just do some basic radial that goes from, I'm gonna make sure that I kind of intersect the 2 curves. So if I do this, what we know is that when we intersect the curves, you're going to intersect the curve here and also the curve here. So we can see that the pink curve is largely radial than the blue curve. So really, the pink curve is going to be our R2, and the blue curve is going to be our R1. Now, I also have to determine where these things intersect. Now, from the image, it's pretty easy to tell it's going to be at the quadrantal angles from minus pi over 2 to positive pi over 2. But if we have to find this algebraically, the way you find intersections is we're going to set them equal to each other. So I have to set this 1 equal to this 1 minus cosine of theta. So this is going to be cosine. So, subtracting 1, 0 is going to be equal to the negative cosine of theta. So 0 is equal to the cosine of theta. And we know that the cosine is, actually it's 0 at the exact same angles, but if you look at a unit circle, the cosine is equal to 0 here, and it's also equal to 0 here. So this is at theta is equal to minus pi over 2 and also positive pi over 2. So now when we set up our integration, we know that the area is going to be equal to the integral from alpha to beta of 1/2 times r2 squared minus r1 squared d theta. And now we know that our r2 squared is going to be 1 squared, so this is going to be the integral from minus pi over 2 to positive pi over 2 of 1/2 times, well, r2 is going to be that 1 squared minus r1, which is going to be that 1 minus the cosine of theta squared d theta. We'll do some simplification and so on. I've already done all the work, and I like to look at it when I'm doing the problems, but there are some symmetries here. Instead of going from negative pi over 2 to positive pi over 2, we could go from 0 to pi over 2 and then double it. So I go from 0 to pi over 2 and double this, which will actually get rid of that 1/2. But I've got the work here, so let's just pretend I didn't see that and then continue. So this is going to be equal to the integral from minus pi over 2 to positive pi over 2 of 1/2 times, well, 1 squared is 1. Now when I square this, we know that this is going to be 1 minus 2 cosine of theta plus cosine squared of theta, and we're still going to have to distribute this negative sign, so really 1 minus this. So let's just simplify this. So 1 minus 1 is going to be 0. This is going to be plus cosine of 2 theta. This is going to be minus cosine squared of theta. So 2 cosine of theta and then minus cosine squared of theta d theta. So we can put our 2's into here. So this is, and then also I wouldn't mind simplifying that as well. So this is the same thing as, minus 1/2 plus cosine of 2 theta all over 2, similar to the problem that we just did before. So this would be minus 1/2 minus cosine of 2 theta over 2. So when we distribute this 1/2 through, this is going to be the integral from minus pi over 2 to positive pi over 2. Half times this is going to be the cosine of theta. 1/2 times this negative 1/2 is going to be minus 1/4. And then 1/2 times, well, this is going to be negative cosine of 2 theta over 2. So this is going to be minus the cosine of 2 theta all over 4 d theta. Which means now everything is integrable, so we can do that. So this is going to be equal to the sine of theta minus theta over 4 minus the sine of 2 theta all over 8, evaluated from minus pi over 2 to positive pi over 2. So evaluated at the top and bottom, so this is going to be the sine of pi over 2 minus pi over 2 over 4 is going to be pi over 8 minus, this is going to be 2 times pi over 2, which is going to be pi, so this is going to be the sine of pi all divided by 8 minus, now when you evaluate this at negative pi over 2, this is going to be the sine of negative pi over 2 minus, this is going to be minus of minus pi over 2, so this is going to be plus pi over 8. And then finally this this minus sine of 2 times negative pi over 2, so this is going to be negative pi all over 8. All right, simplifying these things, what we know is, just look at our unit circle. We're looking at values of pi and also pi over 2. So, and we're doing it for the sine. So this is 0, 1. This is 0, comma, negative 1. So the sine of pi is going to be 1 minus pi over 8. The sine of pi, which is going to be right here, this is 0, comma, sorry, negative 1, comma, 0. So the sine of pi, this is just going to be 0, minus the sine of pi over 2 is negative 1, so this is negative 1 times negative 1, which is going to be plus 1. and this is going to be minus another pi over 8. So finally, when we're done, 1 plus 1 is 2, and then pi over 8 minus pi over 8 is going to be 2 pi over 8, or minus pi over 4. So that's our answer. Now, I did mention that we could also find, say, the area of this crescent. I'll just do it in pink and then kind of discuss it without actually calculating this. So if I wanted to find that pink area instead, well, our limits of integration are going to change a little bit. So remember that we have to open radially. So if I did the pink area, this is going to be pi over 2 all the way to 3 pi over 2. So your limits are going to change from pi over 2 to 3 pi over 2. And also what's going to happen is when you do this radially, let's kind of do our radial curve. If I do my radial, this is going to be the smaller, this is going to be the bigger. So now the blue curve will be your R2 and the pink curve will be R1. So, these limits will change, and then the functions I used before for R2 and R1 are going to be flipped. But you're going to get a very, very similar answer to this. Okay. So that's a good place to stop for this. So I'll see you in a day or two.